This lecture introduces a very important figure in the history of astronomy and physics, and that's the Italian astronomer and physicist Galileo Galilei. Now, you yourselves are probably familiar with Galileo from his very famous observations with the use of the telescope. It turns out, however, that contrary to common belief, Galileo himself did not invent the telescope. The telescope was invented by a Dutch lens maker named Hans Lippershey. Lippershey himself, however, it turns out, probably didn't actually invent the telescope. It was probably discovered serendipitously by a couple of his children who were playing with lenses in his laboratory. If you take lenses and you arrange them in a specific way, this will then magnify images of distant objects. Lippershey himself, however, was the first person to attempt to obtain a patent for the telescope, so then therefore he is given the credit with its invention. Galileo, however, learned about the telescope and realized how it must work, and then built several of his own. The reason why Galileo is so famous is because he was the first to use the telescope for an important reason: to take a look at astronomical objects. Even with modest telescopes such as Galileo's, his optics were not very good, nor were his telescopes particularly powerful. But regardless of the simplicity of his instruments, when you use simple telescopes such as Galileo's to look at astronomical objects, the whole idea of the geocentric universe comes crashing down. So now we take a look at Galileo's observations. All right, so specifically this is around 1609, 1610. Galileo's use of the telescope. He ultimately, by the way, published a book about his observations, and that book made him famous throughout Europe. In part, he built his fortune upon his use of the telescope. Okay, specifically, he began by taking a look at the moon. Incidentally, by the way, he sketched what he saw through the eyepiece of his simple telescopes. Those sketches, of course, were incorporated into his book. He wasn't the greatest artist in the world, but he did get the idea across. Now, when you look at the moon, even with a modest telescope such as Galileo's, immediately you begin to see what can't be anything other than geographical features: mountains, valleys, craters, and so on. Galileo realized what it was that he was looking at when he looked at the moon. So for perhaps the first time in history, we now begin to think of the moon as a place. So we recognized geographical features such as mountains, valleys, and craters. So we now begin to think of the moon, we now begin to think of objects that we see in the sky as places. Okay, then secondly, he looked at the sun. The way that he did this relatively safely was to take sunlight, have it pass through his telescope, and he then cast the image down to a surface below the eyepiece, like a piece of paper or something like that. If you take pains to block most of the light that is entering the telescope tube, this is a relatively safe way to observe the sun. He observed sunspots. Now, of course, he had no idea what sunspots were, but he described them in detail from his observations, and he drew out some detailed drawings of sunspot groupings. We now know today that sunspots are magnetic storms on the surface of the sun. So he's seeing geographical features here, if you will, with respect to the sun. So we now begin to think of the sun as a place. So we observed sunspots. Okay, but then he looks at the planets, and the planets' observations that he made are the ones that are most important. First of all, he looked at the planet Saturn. Saturn is pretty far out in the solar system, and because of that, with a modest telescope such as Galileo's, especially because his optics were poor, he really couldn't see very many details. However, he did see what appeared to be objects on the sides of the disk of the planet itself. He saw, first of all, the planet as a disk rather than as a point of light in the sky. And then he sees objects to the side like so. He described those objects as ears. Of course, he had no idea what it was that he was seeing. Of course, today we understand that what he was looking at were Saturn's rings. The true nature of Saturn's rings weren't really discerned until later on in the 17th century. He was the first to see the rings. As impressive as that is, however, it's really the last two observations that are most important. First of all, Jupiter. Okay, when you look at Jupiter through a telescope, you'll immediately see the planet as a disk, rather than, say, as just a point of light in the sky. And then you see these colored bands going across the planet, like so. We now know today that these are the clouds of the gas giant planet. In addition to that, he was the first to see what is now known today as the Great Red Spot. Once again, he had no idea what it was that he was seeing when he looked at Jupiter, but he did recognize that what he was seeing were geographical features. So now we begin to think of Jupiter as a place. With respect to the Great Red Spot, we now know today that it's actually a hurricane. It's a hurricane that has probably been raging for thousands of years, if not longer, and even though the size of the red spot does vary over time, on the average it's about 3 times the diameter of the Earth. So imagine a hurricane that is that large, raging for centuries and beyond in the atmosphere of Jupiter. As impressive as those observations are, even more importantly with respect to Jupiter are 4 spots of light that Galileo observed close to the planet. So here's the planet like so, and there are these 4 spots of light. They are arranged into a plane. And then even over the course of just a couple of hours, and then certainly from night to night, if you observe those spots of light, you're going to see their relative positions change. So for example, let's say that you look at the planet one night and it looks like this, and then the next night you look at it again and it looks like this. Like so. The relative positions of those spots of light has changed. What Galileo realized that he was looking at were now referred to as the 4 major moons of Jupiter. These are referred to as the Galilean moons or the Galilean satellites in Galileo's honor. Galileo realizes that what he is seeing here is celestial motion, motion in the sky that is definitely not centered on the Earth. That's why this observation is so important. And he also sees a similarity between Jupiter and the Earth. The Earth has a moon, Jupiter has at least 4 moons. Therefore, the Earth and Jupiter are similar objects. Objects that are planets, for example, that are orbiting the sun. So we're now starting to see direct observational evidence that Copernicus is correct. So these are the major moons of Jupiter. And this is the first direct evidence of celestial motion that is definitely not centered on the Earth. That's why this particular observation is so important. The clinching evidence, however, that Copernicus is correct, that all of the planets, including the Earth, orbit the sun, however, comes when you observe the planet Venus. Let me do some erasing here. If you watch Venus through a telescope over the course of weeks and into months, you'll see it go through changes in appearance. It changes its appearance a couple of different ways. Number one, you're actually going to see it go through a set of phases, much like the moon. You're also going to see it change its relative size as seen through the telescope as well. For example, let's say that we begin this process by observing Venus in the early evening hours, so just after sunset. And as you begin to observe Venus, you see it do the following. Okay, so now it's just after sunset. You'll begin by seeing Venus as small through the telescope, and you'll see it as a gibbous phase, which looks like this. And then let's say you look at the planet again a couple of weeks later. When you see it again a couple of weeks later, you're going to see it as larger in the field of view, and you're also going to see it as a quarter phase. It's going to look like this. Okay, a couple of weeks after that, it's larger still in the field of view, and it shows up as a crescent. Like so. So as I draw out this simple diagram, basically time, if you will, is going in this direction. Okay, and then there's a period of a couple of weeks or so where you actually can't see the planet at all. And then all of a sudden you could start to see the planet before sunrise. And when you first see the planet, you're going to see it as a crescent once again, but the crescent is on the opposite side of where it was previously. Like so. So here's darkness, like so, and there's daylight on the left. A few weeks after that, it's smaller in your field of view, and it looks like a quarter. A few weeks after that, it's smaller in the field of view, and it looks like a gibbous. Notice these drawings, however, are backwards of what they were previously. In this case, time is lapsing in this direction, and then from left to right on this simple diagram, there's a period of time here where the planet is not visible. Galileo realizes that the only way in which you could explain these observational facts about Venus is that Venus is orbiting the sun closer than the Earth is. On this portion of the diagram, Venus is catching up to us in its orbit. It's closer to the sun than we are, so then therefore it moves faster in its orbit. During this period of time here where the planet is not visible, basically the sun's in the way. In other words, the planet is basically at inferior conjunction. And then after that, the planet then recedes from us on the other side, getting smaller and smaller as it does. This may be initially a little bit difficult for you to picture. So then therefore, as I conclude this lecture on Galileo's observations, as a follow-up, you are now to do the following. Watch a screencast that I have posted for you called Galileo's Observations. I show you the drawings that Galileo made in making these observations, and you'll also see some nice graphics towards the end of that screencast that very nicely depicts this situation and why it proves that Copernicus was correct. So at this point in the lecture, we basically now have two things, if you will. That is, we have Galileo's observations that I just described, and we have Kepler's laws of planetary motion. Kepler's laws of planetary motion mathematically describe how the planets orbit the sun. Backing all of that up, however, we now have Galileo's observational evidence.